Hey everyone, welcome back. D.9. This video is focusing on Newton's third law of motion. One of my favorite topics in AP Physics 1 because at first glance this law seems pretty straightforward. I'm actually assuming that a lot of you could actually recite a version of it right now, but there are absolutely some difficult, some tricky applications to Newton's third law. So yeah, there's knowing it at kind of first glance, at first recital, but really understanding the nuances, it can lend itself to some very interesting and some challenging problems. So here we go. Let's get into it, all right? Like I said, I'm guessing a whole bunch of you already know a version of Newton's third law, and here's a definition. It says, for every action, there is an equal and opposite reaction. And when I hear that, and when I see that on slides, I think, oh my gosh, what an absolutely terrible definition for a physics concept. Okay, this has to be one of the least clear descriptions of some kind of phenomena that I've ever heard in my life. And to be honest, that definition, how it's written right there, isn't too different than Isaac Newton's own Latin version. So even Isaac Newton himself, oh my gosh, did such a terrible, completely garbage version of an explanation for this law. I can't believe it. This is just the absolute worst. Why? What the heck does this mean? For every action, there's a reaction. What the heck is an action? What is a reaction? What are they talking about? Okay, equal and opposite. Where are these actions and reactions happening? Within an object? Spread out between multiple objects? Between things? I have no idea what this means in its current form. This definition is absolute trash. So let's learn the proper way to think about Newton's third law. Here it is. This is the better definition. Okay, now we're going to hear and see what we're talking about. It says when one object exerts a force, we know what a force is, on a second object, the second object exerts an equal and oppositely directed force on the first object. This is 1,000 times better. So it's talking about two different objects. So here's object one, here's a person. Here's object two, here's a wall. Okay, we're dealing with two different objects. The other thing Newton's third law is talking about is obviously forces. It says when this person applies a pushing force, now let me change to red, okay? When this person pushes on the wall, so if I think of a free body diagram for the wall, there'd be a force to the right. I mean, there's surely other forces, but let's just simplify it here. All right, according to Newton's third law, it says when this object exerts a force on the second object, the wall, exerts an equal and oppositely directed force back on the first object. Oops, sorry, that should be a horizontal line. So if I made a now free body diagram for this person, there'd be a force like this. This is what Newton's third law is saying. It's discussing two different objects, okay, a wall and a person in this diagram. And it says when one is exerting a force on the second, that second object is pushing back, so to speak, exerting an equal and opposite force back on the first. Now we understand. It's between objects and it's dealing with forces. What are some examples, okay? Here's an example when you fire a gun, all right? Well, maybe if you're familiar with firing a gun, or of course if you watch enough movies or see YouTube videos, you might be familiar with the idea of kickback, okay, of recoil of a gun. When you fire a gun, when you fire a bullet, okay, there is a large force applied to the bullet. If we drew a free body diagram for a bullet, again, let's just focus on the maybe force from the gunpowder, there'd be a huge force applied to the bullet. Well, by Newton's third law, in fact, the bullet applies an equal and opposite force back on the gun. That's why you get kick from a rifle, why you get recoil from a gun or from a cannon, something like that. Because of Newton's third law. There's a big force on the bullet to the right in this picture, and by the third law, there's also a big force to the left on the rifle. Same thing, maybe you see some funny videos of people trying to get off of boats or something, and they end up falling into the water. Okay? This person is trying to move forward, so by pushing off of the boat, they're getting a force acting on them this way, but of course, they're applying an equal and opposite force on the boat, which tends to, again, if you watch some maybe funny YouTube videos, makes that boat push backwards, and then all of a sudden, there's a big gap between them and the dock. Or think of a rocket, okay? What is being pushed on in a rocket? It's actually the gas, it's the exhaust that's coming out of the rocket. all those billions upon trillions of atoms and molecules, all that exhaust, all that fuel, there's all this force being applied on those gases, those atoms and molecules. And by Newton's third law, the gas, those molecules, apply an equal and opposite force back on the rocket. So force is on the gas, an equal and opposite force on the rocket. That's why when you're launching a rocket, you always have to be pushing the exhaust in the opposite direction. Okay, we'll maybe see some more examples of that in my own physics class. Also similar, it's maybe a little difficult to zoom into the details. If you blow up a balloon and you let it go, the balloon gets force. It goes flying off in a direction because it applies a force on those air particles as it squeezes, as it pushes them out of the balloon. And by Newton's third law, those air particles are applying an upward force on the rubber, on the latex of the balloon itself. Okay, so at the most basic level, people think Newton's third law is a piece of cake. And it's almost like, why am I spending already 5 minutes on this? Let's get into some new ones. Here we go. Here's a scenario, an example third law question. I have a small truck, a relatively small truck, and it's going to crash into a much larger van. I guess it says a small car. I know this is a truck here, but this is a much bigger truck. Heck, let's say that this is a truck of mass m, and this is a truck of mass 100m. This is 100 times more massive. And it says this truck has a velocity that's 10 times faster. Okay? A small car crashes into a large truck driving 10 times faster. So this big truck is going super fast. It has way more mass. It's going way faster. Which experiences a greater force? And the answer is neither. The force on each of these trucks is the exact same. It has to be by Newton's third law. This truck applies a force on this white truck, and by Newton's third law, the exact same force must be applied to the other one. Okay? Who cares if one has more mass? Who cares if one is moving faster? Now, Newton's third law is not telling us what's going on, say, with the rapid deceleration of these trucks. It's not describing the displacement of these trucks or the ending velocity of these trucks. It's just talking about force. And always, if the forces are the same, well, one cannot be larger than the other. Likewise, let's scale this way down. Let's assume maybe these aren't moving at all. Let's say I got my big truck, it's not even moving, and instead of being collided with a big red truck, let's say it's colliding with a fly. Can I draw a fly? Buzz, buzz. So here's a little fly. It was just kind of floating around. Let's say that fly buzzes around and slams into that truck. Which experiences a larger force? The fly, which is surely dead, slamming into the truck, or the truck, which would have zero damage? There is no difference. They experience the same force. They have to by Newton's third law. The fly exerts a force on the truck must apply an equal and oppositely directed force on the fly. So it would look like this. Here's a force on the truck, here's a force on the fly. Newton's third law is only comparing forces, not the mortality or the damage of the objects, because that might depend on other things like the acceleration or the mass, things like that. Maybe Newton's second law comes into play, and we'll get more practice with that. But these forces must always be equal and opposite. Let's do another example. This is one of my favorite physics examples, okay? I'm going to read it, and I'm actually going to recommend you hit pause and try and explain this on your own. This is really going to be the last 3 or 4 minutes of this video, this example right here. It says, okay, we have this horse pulling a cart. And, you know, this horse is like, all right, I guess I've been all set up here. I'm attached to this cart. I'm about to do some manual labor. But luckily, this horse is pretty smart, it thinks. And the horse thinks to itself, wait a minute. If I try and pull the cart forward, if I try and pull a force, if I try and apply a force on the cart, well, wait a minute. By Newton's third law, there's going to be an equal and opposite force backwards. Because Newton's third law says if there's a force acting to the right, there should be an equal and opposite force going to the left. So by Newton's third law, there will always be an equal force in opposite directions. Therefore, the horse says, I'll never be able to get the cart moving since these forces will cancel out. Huh, that's weird. What do you think? Is this an accurate description of what's going on? Yes? Why? If not, what's the problem? Hit pause. Think about it for a second. Now, to be honest, even if you're like, well, what about Newton's second law? If you set up Newton's second law, isn't this going to prove the horse is right? Because if there's a force acting to the right, and according to Newton's third law, there's an equal and opposite, meaning maybe +5 combined with -5, doesn't that mean the net force, which equals ma, is going to equal 0? So the horse and cart never accelerate? Now, surely this can't be true, right? Because, have you seen ever on a movie or TV show, or maybe in real life, a horse moving a cart? Of course. You can push the table that's sitting in front of you. But where's the flaw in this? Because it seems like they're talking a lot of good physics. You push on the table, isn't there an equal and opposite force backwards to cancel that force? So shouldn't that mean you can't move the table? If you're thinking to yourself, well, yeah, but maybe you push more on the table. So what? If you push more on the table, by Newton's third law, the table should push back more on you, still canceling out. There is a solution to this seeming paradox. And what is it? The explanation is, do you understand the nuance of Newton's third law? This diagram, how it was originally shown, and I'll erase my little markings, is very unclear. And when I had my 2 lines, a little bit on purpose, it's deceptive. This is really the application of Newton's third law. Here's what the horse is saying. The horse applies a force on the cart. The horse is pulling the cart to the right. Newton's third law does not say there is a canceling force on the cart. Newton's third law says if the horse applies a force on the cart applies a force on the horse. There is no canceling because these forces are on 2 different objects. I have the cart with one force to the right and the horse with a force to the left. Nothing's canceling. When I do the sum of the forces for this cart, I still have a force acting to the right. Newton's third law says these forces are on different objects. Oh, students always get tripped up by that. That's why things are canceling. So how is the horse able to move the cart? Well, the horse applies a force, okay, and that force is able to get this cart rolling. But wait a minute, maybe you're thinking, well, how come the horse doesn't accelerate backwards, right? Because isn't there this backward force on the horse? Absolutely. But the horse has feet, and those feet are digging into the ground. The horse has good friction, good traction. Just like your shoes, if you try and push on a table, you're not going to go flying back, maybe unless you were wearing, say, roller skates. If you had roller skates on and you push on a wall, you would go backwards because you apply a force on the wall applies a force back onto you, and you would accelerate backwards. But because the horse has some good traction, that will cancel the force from the cart. Notice, to understand Newton's third law, you have to realize we're looking at different objects, and maybe to understand whether something is going to move or not, you might have to take into account other forces as well. Okay? Very important. So there are some tough problems. I haven't even gone over one of my personal favorites in this video, because if you're in Mr. Thrasher's class, I'm going to kind of show you that a little bit later. But Newton's third law, at first glance, it's really straightforward, but make sure you really understand what it's saying, because if not, you're going to be caught up in some tricky questions by your teacher, your professor, or by the AP Physics 1 exam. Okay? That's it. That's all for this video. I appreciate you watching.